Hello everyone, this is the second half of the review for test 2. I'm going to start with problem number 26. In a survey of customers aged 12 and older, respondents were asked how many cell phones were in use by the household. Among the respondents, 214 answered none, 295 said 1, 369 said 2, 147 said 3, 94 responded with 4 or more. A survey respondent is selected at random. Find the probability that his or her household has 4 or more cell phones in use. Is it unusual for a household to have 4 or more cell phones in use? Consider an event to be unusual if its probability is less than or equal to 0.05. Remember that right there, that 0.05, that's like 5%. So if your probability is equal to or less than 5%, then it's unusual. If it's greater than 5%, then you can just say that it's usual. Alright, so if we want to know if it's unusual for a household to have 4 or more cell phones in use, notice only 94 responded with 4 or more. So you find the probability by saying 94 divided by the total number of cell phones. So you have to add up, the 214, 295, 396, 147, and 94. Add all that up and you get 1,119. Divide that, and once you round, you do get 0.084. That's that. Is it unusual for a house to have 4 or more cell phones in use? And the answer to that would be no, according to this study, because 0.084, that's bigger than or larger than 0.05. So since that's larger, then it's not unusual. Another way to think about it, remember I said this is 5%, this would be 8.4%. So if 8.4% is larger than 5%, then it's just usual. Right, and this problem asks, is it unusual? So no. Because the probability of a respondent with 4 more cell phones in use is greater than 0.05. Alright. If a couple were planning to have 3 children, the sample space summarizing the gender outcomes would be, so this is the different ways you could have the children. Boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. Alright, that's the ways that you could have 3 children, boys and girls. Part A says, construct a similar sample response for the possible gender outcomes using B for boy and G for girl for 2 children. So just 2 children. So say you're going to have 2 children, then you could have a boy and then a boy and then a girl and then a boy, or a girl and a girl. There's 4 different ways if you have 2 children. And that's what they have listed here. Find the probability of getting 2 children. Okay, so it does say assume that the outcomes are likely. So find the probability of getting 2 girl children. So there's only one case that you would have 2 girls. That's girl, girl. So that's one way out of a possible 4 different ways. So the probability of 2 girl children is 1/4. 1 out of 4. Find the probability of getting 1 boy child or 1 girl child. Alright, so there's boy girl and there's girl boy. So there's 2 possible ways to do that out of the 4 total. That reduces to 1/2. that's why the probability is 1/2 there. Alright, moving on. What is wrong with the expression probability of A plus the probability of not A equals 0.5? If you recall from the previous video that I put up, I said that the probability of something happening plus the probability of it not happening has to be equal to 1. So that's what's wrong there. That's not equal to 1. Based on the rule of complements, the sum of probability of A and probability of not A must always be 1, so that the sum cannot be 0.5. Alright. Decide whether the following two events are disjoint. So what are disjoint events? Things that can't happen at the same time. Okay? So we need to know, are these two disjoint? Right, randomly selecting an animal with green eyes, randomly selecting an animal with brown eyes. So can you select one animal that has both green eyes and brown eyes? Now if that would have been eye, yeah, you probably could find an animal somewhere in the world that has like one green eye and one brown eye. But we can't find an animal if we select one animal that has both green eyes and brown eyes. So that means that the two events are disjoint. Okay, and the answer is yes, because the events cannot occur at the same time. A research center poll showed that 81% of people believe it's morally wrong to not report all income on tax returns. What is the probability that someone does not have this belief? Now remember, we said that the probability of something occurring plus the probability of it not occurring is equal to 1. So if the probability showed that 81% believe that it's morally wrong, then what is the probability someone does not have this belief? So the probability of having the belief, so probability of belief, is equal to 81%, and that's 0.81 as a decimal. So the probability of not having a belief, what would that have to be equal to? Well, if we know the two probabilities have to add up to be 1, then the probability of not belief would be 1 minus 0.81, and that's 0.29. I'm sorry, no, not 29, 0.19. It's 0.19. Because whatever answer that I get out to the probability of not having the belief, when I add that back to the probability of the belief, that has to be equal to 1. Make sure you use a calculator so you don't make a mistake like I did. The following data summarizes results from 100 pre-employment drug screening tests. If one of the test subjects is randomly selected, find the probability that the subject had a positive test result or a negative test result. That's kind of like saying what's the probability that it's going to rain today or the probability that it's not going to rain today. So that's something and its complement. There's really no work to do on here because the probability of something happening plus the probability of it not happening is always equal to 1. So there's not any work to do, it's just 1. Alright. Let's see, the following summarizes results from 929 pedestrian deaths that were caused by accidents. If one of the pedestrian deaths is randomly selected, find the probability that the pedestrian was intoxicated, or the driver was intoxicated. So, the probability that the pedestrian was intoxicated, see here's the pedestrian, so these right here, these two, the pedestrian were intoxicated. Right. The probability, let's see now, that the driver was intoxicated. The driver was intoxicated are these two. The driver, now 69 and 75. So 69 and 203, 69 and 75. We don't want to add this 69 twice because it belongs to both groups. So we'll say probability of pedestrian was intoxicated or driver was intoxicated will be equal to, so pedestrian we said 69 plus 75, and then driver being intoxicated was 69 plus 203. Again, we don't say the 69 twice, so it's just plus 203. Divide that by a total number. That was 929. Okay. So 69 plus 75 plus 203 divided by 929. And if we round that to 3 decimal places, that'll be 0.374. So 0.374. Given that 2 of the 173 subjects are randomly selected, complete parts A and B. Assume that the selections are made with replacement. So that means we're going to select something, get a probability, then we're going to replace that, and then we'll select something else. Okay? What is the probability that the two selected groups are both AB and RH positive? Notice that those overlap. So we want to make sure that we don't, or that we only choose the one that overlaps. Here's what I'm talking about. Alright, so the probability that the two selected are both AB and RH positive. So these two are AB, these two groups. This is RH positive. We want the probability of both of those occurring. Alright? And also we're selecting 2. The first time we're going to select with replacement. So to find this probability, we're going to say, okay, again, what are we selecting? The one that is AB and RH positive. So that's 9 out of 173. And since this said with replacement, then we replace that person and randomly select again. 9 over 173. Alright, so it's 9 times 9 divided by 173 equals, divided by 173 equals. We round this to 4 decimal places. It's 0.0027. It's about 0.0027. That's part A. Part B, the only difference is without replacement. So we'll do the same thing, except so the first time we select, it's going to be 9 over 173 chance. Now we're not going to replace that person. So that means that the next time there's only going to be 8 of those possible, and there's not 173 people because we didn't replace that person. It's 172. So when we have without replacement, usually we have to change the number of what we're selecting to 1 less and the total number of the group minus 1. So let's work that out. This will be slightly different. And if I round this to 4 places, 0.0024. Alright, the principle of redundancy is used when the system reliability is improved through redundant or backup components. Assume that a student's alarm clock has a 15.4 daily failure rate. So I guess that means 15.4% of the time the student's alarm clock doesn't go off. I bet he got cut out, or she got cut out of class pretty quick with that. But anyway, let's see. What is the probability that the student's alarm clock will not work on the morning of an important final exam? So it says as a decimal, so that'd be 0.154. There. If the student has 2 such alarm clocks, what is the probability that they both fail on the morning of an important exam? So 2 alarm clocks, the probability that the first one fails is 0.154, and the probability that the second one fails is 0.154. So for both of those to occur at the same, on the same morning, the same time, you multiply. So that's 0.154 times 0.154. Ooh, that significantly drops the rate. Round to 5 decimal places. 0.0237. So 1, 2, 3, 4, 5. So 0.02372. So that's 2.3%. So that's a lot better off than 15.4%. Okay. Let's look at the next part. What is the probability of not being awake if the student uses 3 independent alarms? So 3 just means we add another. So 0.154 times 0.154 times 0.154. .00365 if you round to 5 decimal places. So what does that actually mean? That means that there is a 0.3% chance of that occurring, of that student oversleeping. So that's even, that's like 3 out of 1,000 times. So that definitely will make sure that he gets up more than likely anyway. Do the second and third alarm clocks result in greatly improved reliability? I think it's a pretty big difference to go from 15% to 2% and then to 0.3%. So yes, because the total malfunction would not be impossible, but it would be unlikely. Okay. The reason this one was wrong is the answer is yes, but it says because you can always be certain that at least one alarm clock will work. No, you can't be certain, but it's something that, you know, it's just not very probable. Number 35. The data in the table below summarizes results from 138 pedestrian deaths that were caused by accidents. If two different deaths are randomly selected without replacement, find the probability that they both involve intoxicated drivers. So without replacement, they both involved intoxicated drivers. So look at the intoxicated drivers here. Okay, so we have 40 intoxicated drivers, and was the driver intoxicated here as well? Yes, for both of these, 40 and 27. Driver intoxicated, yes. So that's 67. So it'll be 67 out of 138. And then if we do this without replacement, that means the next time we'll have 66 out of 137. I'm going to tell you on this one, I worked it out, and you'll see what I get. 67 times 66 divided by 138 divided by 137. I got 0.2, it'll be 0.234 when I round. This right here says the correct answer is 0.236. And so what I did is I pulled this same problem up and I worked it out 4 more times. Every time that I worked it out with different numbers, it came up correct. But this one time, it didn't. So what I'm going to do is I'm going to check all of your tests on this one. And if you're just off by like 1,000th or 2,000th like that, then I'm going to give you credit on this one. I think this was just an anomaly where, for some reason, this answer wasn't right. It's just off by a little bit. And we will know, is such an event unlikely? That's 23.6% of the time. So, no, that probability is definitely greater than 0.05. Remember, that's 5%, that's 23.6%. So that's way bigger than 5%. So it is not unlikely. Okay. Determine the written description of the complement of a given event. When 5 cameras are tested, at least one of them is defective. So think about at least one. At least one would be 1 or 2 or 3 or 4 or 5. So the opposite of that, the complement of that, is none. The complement of at least one is none. So that means the complement of none is at least one. Works both ways. Okay. Determine the written description of the complement of the event. When 5 cell phones are received, all of them are free of defects. So the complement of all, in this case, is going to be at least one of them is defective. Okay. The complement of all is at least one. Right, if a couple plans to have 4 children, what is the probability that there will be at least one boy? Assume boys and girls are equally likely. Alright, so the easiest way to work this problem is to think about the complement. Alright, let me show you how I see this. So we want the probability that there will be at least one boy. Well, what if we looked at its complement? The complement of at least one would be no boys. That's the complement, okay? So that right there is probability of at least one not. Okay? Remember what we said about complements. The probability of A plus the probability of not A has to be equal to 1. So what that means is the probability of A is equal to 1 minus the probability of something not happening, not A. So what we can do to find the probability of at least 1, because, I mean, what does that actually mean? If we work this out like this, that's the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4. So instead of working out all of those problems, what you could do is figure out the probability of no boys, so that would be 4 girls, right? So the probability of having 4 girls, you have 4 births, 4 girls, the probability is going to be 1/16. So that means that is the probability of no boys, 4 girls. So I can say 1 minus 1/16 and get this answer. Probability of at least one boy equal to 1 minus probability of no boys. 1 minus 1/16, and that's 16 over 16 minus 1 over 16, that's 15 over 16. To me, that just makes more sense to use the complement. The other way, you would have to figure out the probability. You'd have to list out the sample space, and then you'd have to figure out the probability of 1, the probability of 2, the probability of 3, and the probability of 4, and add all those together, and you would get 15/16. It would just take a lot longer. Alright. Can the couple be very confident they will have at least one boy? Yes, because that is close to 1. And I'm sure you, as well as I, know cases where, a family has 4 girls, or I know one family has 5 girls and no boys, so it does happen. It's just rare. Find the probability of having a baby girl when their 4th child is born, given that the first 3 children were all girls. Now you would think, if you have 3 girls, the probability of having another girl would be rare, but that's not what it's, that's what it's asking actually, of, you already have 3 girls. What's the probability of having a 4th girl? Well, the probability of having a boy or a girl is right around 1/2. So it is 1/2 if we assume that they're equally likely. It doesn't matter that you had 3 girls before. Probability-wise, we say that it's still 1 out of 2 chance. Now, that would be different if we wanted the probability of having 4 girls. Girl, 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 girl. That's only 1 out of 16. This question kind of relates to that. Is this result the same as probability of getting all girls? No, it's not. Because we were told, given you have 3 girls, what's the chance of having a 4th girl? That's different than the probability of having 4 children and all of them being girls. That's a 1 in 16 chance. Okay, so no. The second event involves more possible outcomes. Probability of randomly selected car crashing during a year in a certain country is 0.0475. If a family has 3 cars, find the probability that at least one of them has a car crashing during a year. At least one is the key right there. Because if we know something at least one, then we probably want to use the complement. Because at least one would mean 1 crashing, or 2 crashing, or 3 crashing, and that would take a lot of work. So we want the probability of at least one of them crashing. I'm just going to say at least one. Remember, that should be equal to 1 minus the complement of at least one. Complement, remember it's got to be the complement. And what is the complement of at least one? That would be the probability of none. Okay? So we were told that the probability of crashing is 0.0475. So what will be the probability of one car not crashing? If the probability of crashing is 0.0475, the probability of not crashing is 1 minus 0.0475. So this is just 1 though. Okay? And this is the probability of no crash. So that'll be 0.9505. These two, even though I wrote none and probability of not crash, that means the same thing. The only thing is, the probability of none, I guess it's not exactly the same, because the probability of none, this means the probability that none of the cars at all will crash, and you have 3 of them. So what you're going to have to do is say 1 minus 0.9525 cubed. Okay. If it was just for 1 car, we would say 1 minus 0.9525. For 2 cars, we have to write it twice. 3 cars is just cubed. Again, the probability of at least 1 crashing is equal to 1 minus the probability of not at least 1, which is the probability of none of them crashing. So, put that in the calculator, 1 minus 0.9525 cubed. I'm just going to cube it. Alright, so that's what I get if I cube 0.9525, but I need to subtract that from 1. So what you could do is just make this negative and then add 1 to it. So that gives you, rounded to 4 decimal places, 0.1358. 0.1358 is your answer. 0.1358. The data represent the results for a test for a certain disease. Assume one individual from the group is randomly selected. Find the probability of getting someone who tests positive given that he or she did not have the disease. Alright, so that second part there, given that he or she did not have the disease means, alright, look, did the individual have the disease? No. Or yes. Given that they did not have the disease means we're just considering these here. That's given. So if this is given, we want to know the probability of someone who tests positive given that. So this is given, but we want to know positive given this. So there's 19 that are positive. There are 19 plus 136 that did not have the disease. So the way that we find the probability of A given B, that's what that is. Probability of A given B. So the probability someone tests positive given they did not have the disease from our table, did not have the disease was 19. I'm sorry, tested positive was 19. Did not have the disease, 19 plus 136. It's 19 divided by 19 plus 136. And you should get about 0.123. .42. Find the positive predictive value for the test. That is, find the probability that the subject lied given that the test yields a positive result. Positive result here. Probability subject lied here. So 44 divided by 14 plus 44. Alright, so work that out. You're going to get about 0.759. Alright, now, moving on to 43. I believe the rest of these problems are on permutations and combinations. So, cookies, yeah. We want to go counting permutations and combinations. Does order count? So it's very important that we understand the difference between these two before we get started. In these next couple problems. Permutations. The items are arranged in different sequences of the same items are counted separately. I'm sorry, I think I messed it up. Permutations of items are arrangements in which different sequences of the same items are counted separately. For example, with letters ABC, the arrangements of ABC, ACB, BAC, AC, blah, 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 were all counted separately as 6 different permutations. Okay. Combinations are arrangements in which different sequences of the same item are not counted separately. For example, with the letters ABC, all these arrangements are considered to be the same combination. That does mean that combinations will always be smaller than permutations. So look at this mnemonics right here. This may help you understand or remember. It says, when trying to remember which of the 2 preceding terms involves order, think of permutations position, where the alliteration reminds us that with permutations, the positions of the items makes a difference. You might also use the alliteration in combinations committee, where those words remind us that the members of a committee Rearrangements of the same members result in the same committee, so order does not count. So order does not count with combinations, it does with permutations. Alright. You might want to read that like 6 times or so because they can run together. Alright. In horse racing, a trifecta is a bet that the first 3 finishers in a race are selected. So you gotta not only get the 3 top, you have to select them in the order that they're selected or that they come in. So does a trifecta involve combinations or permutations? If order didn't matter at all, then it would be a combination. But order does matter. Because the order of the first 3 finishers does make a difference, the trifecta involves permutations. So order does matter. When an ATM thief steals an ATM card and must randomly guess the correct 7-digit PIN from a 5-key keypad. Repetition of digits is allowed. What is the probability of the correct guess on the first try? Okay. Now, I like to, and most of these problems are combinations and permutations, but sometimes you can just kind of put it in common sense. Put a little common sense in your problem, like, think about, if you can repeat the digits, you have 7-digit PIN, so that's 7 chances. And it says it's from a 5 keypad, so you only have 5 keys. Now we don't even have to know if they're numbers or what, they could be symbols, it doesn't matter. Well, we're going to have 5 choices here, and 5 choices here, 5 choices here, and so on and so forth. So that's 5 to the 7th power. And that's going to give us 78,125. The probability that the correct code is given on the first try. Well, the first try only happens once. So the probability that it's going to happen on the first try is 1 out of 78,125. A fan of country music plans to make a custom CD with 11 of her 26 favorite songs. How many different combinations of the 11 songs are possible? Is it practical to make a different CD for each possible combination? So this tells us it's a combination. So how many different combinations are possible? Combination, the formula for combination is NCR, where N is the number of items total, R is the number selected. It's going to be 26 factorial over 26 minus 11 factorial times 11 factorial. But why? Alright, there's this top here is n factorial. Probably should have wrote that first. I'm going to write that beneath it here. It's n factorial, so total number over total number minus the actual number you're selecting, factorial over the number you're selecting, factorial. Alright, so if you're not familiar with factorial, let me show you what factorial means. factorial gives you really, really big numbers. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. You can see 5 factorial, that's what? 120. It doesn't take very far. With 6 factorial, 7 factorial, 10 factorial, the numbers are going to get larger and larger and larger really quick. So you want to be careful, and maybe just let your calculator do the work. That's the best thing on these. Even though your calculator may show you scientific notation, that doesn't mean that it's going to just store it as scientific notation, or it's not going to round on you. It shouldn't anyway. So this would be 26 factorial over 15 factorial times 11 factorial. But make sure that you use the little exclamation point button to get your factorial. So 26 factorial. You see it's so big. I mean, this isn't in scientific notation, but most calculators only take it out about 6 places. So that's 26 factorial. And you divide by 15 factorial. 15 factorial. Then take that and divide that by 11 factorial. And that's still a big number. That's 7,726,160. So that means that's how many combinations of those 11 songs are possible. Alright. Is it practical to make a different CD for each possible combination? You could start making CDs today, and I don't know if you could make 7,726,160 CDs before your computer broke. So, just think about how long it takes to make 1 or 2 CDs, let alone in the millions. So, no, that's not very practical. That's just too many. The number of possible combinations is very large. 46. A presidential candidate plans to begin her campaign by visiting the capitals in 3 of 46 states. What is the probability she selects the route of 3 specific capitals? It's a probability, so know that it's going to be 1 out of whatever we find. Okay, and since there are 46 states, and we want to know the probability of her selecting the route of 3 specific capitals, that's 3 of the 46. Okay, so that's going to be a permutation. So 46 is going to be, like I said, a permutation. Let me show you in your book where the formulas for permutations are. And there's an explanation on permutations in your textbook. So permutations is n factorial over n minus r factorial. Combinations is not given. Combinations, yes, right here. N factorial over, it's supposed to be n minus r factorial. You see? I don't see why they have a 1 here in your book. So that's wrong. It's supposed to be an r. That's a typo. Good thing. So look at your formula sheets. That's n minus r. It's not a 1. For some reason I have it as a 1. We will have to use this other formula up here too if we're looking for, we're looking at like a number of items where some of the items are repeated. Then we'll have to use this formula right here. N factorial divided by n sub 1 factorial times n sub 2 factorial, so on and so forth. That's if you're selecting n number of items and then some of your items are repeated. Okay. We'll get to that though. So that's the three main formulas, and the two main ones are the one for permutations and one for combinations. So on this one, we said we had 46 states, so that's our n, so it's 46 factorial, and we're taking 3, so 46 minus 3 factorial. Okay. So I can show you a way how to do this a little quicker. You can punch it in your calculator, but if the number gets too big with factorial, sometimes your calculator may just freak out on you. So what you could do, remember that's 46 times 45 times 43, so on and so forth. So if we wrote the numerator as 46 times 45 times 43 factorial, stop there, over 43 factorial. So if you stop at the number, then you just put a factorial behind it. So now you see those cancel out. And so, you know what? I left my 44. So that's 46 times 45 times 44 times 43 factorial. I apologize for that. So that's 46 times 45 times 44. If you do that in your calculator, you get 91,080. Alright, so we want to know the probability of going that one specific, or that route. It's just one out of that, one out of 91,080. Okay. Is it practical to list all the different possible routes? I couldn't see anybody listing out 91,080 routes, so the answer is no. A classic counting problem is to determine the number of different ways that the letters of misspell can be arranged. Find that number. So that's 8 different letters. Notice that some of the, not 8 different letters, but 8 letters. Notice that some of the letters are repeated. So this is where we would use the permutation formula where we have some things that are repeated. And that was n factorial that was n factorial divided by ever how many you have repeated factorial times ever how many you have repeated factorial, so on and so forth. So for this one, if there's 8 different letters, it's going to be 8 factorial over, alright, you have, in the word misspell, which I do a lot, you have 2 S's and you have 2 L's. So we're going to divide this by 2 factorial for 2 S's, 2 factorial for 2 L's. Alright, so it's going to be 8 times 7 times 6 times 5 times 4 times 3 times 2 factorial divided by 2 factorial times 2 factorial. So that will cancel one of those out. The only thing else I have to do, I have to say 8 times 7 times 6 times 5 times 4 times 3 times 2. And then divide that by 2. Because 2 factorial is equal to 2. When you do that, you should get 10,080. 47. Find the probability of winning a lottery with the following rule. Select the 5 winning numbers from 1 to 36 in any order. No repeats. So if it's no repeats, what does that mean? That means that this is a combination. Remember, we're taking 5 of the 36. So if we're taking 5 of the 36, and this is a combination, so it's going to be 36C 36 factorial over 36 minus 5 factorial times 5 factorial. Alright, so you can simplify this like we did up here, or you can just trust your calculator and say 36 factorial divided by 31 factorial, then divide by 5 factorial. Let's see what my trusty calculator tells me. 36 factorial. Whoa! You see, they had to put this in scientific notation. It was so big. Divided by 31 factorial. It should bring it down. Divided by 5 factorial. So I get 376,992. Let's see, what was the question actually asking me to do? The probability of winning. Well, there's only one way to win. So if this is the total number of ways, there's only one way to win. So it's 1 out of 376,992. Corporation must appoint a president, chief executive officer, chief financial officer, chief operating officer. Alright, so there's 4. Don't really care about their titles, I just know there's 4. Okay, that's one of the main things. Okay. It must also appoint a planning committee with 4 different members. The 14 candidates, there are 14 qualified candidates, and officers can also serve on the committee. Okay, complete parts A through C below. How many different ways can officers be appointed? Okay, so think about it though. The way that I appoint those 4 people, maybe it's, say, for president, CEO, COO, and CFO. So one way would be like, say, me being the president, you being the CEO, let's say your friend being COO and my friend being CFO. Now we could select those same 4 people and just put them in different positions, and that's different ways, right? Because if you're the president, I'm the CEO, your friend's COO, and my friend's CFO, that's different. You know, it'd be another different way with those 4 same people. Let's say your friend was president, my friend was CEO, I was COO, and you were CFO. So all of those are different. The arrangements are different. Okay? So that makes that a permutation. Because they're different. Like the same 4 people being in those positions, being in different positions, would actually make the group different. Okay, so that's part A. It's going to be a permutation. So that's going to be 14 factorial over 14 minus 4 factorial. Because we said that we were selecting 4 of those. N factorial over n minus r factorial. So that's 14 factorial divided by 10 factorial. We could let the calculator do that. Or remember the way I told you could simplify this. You just keep stepping down until you get to that bottom. Once you get to the bottom there, you can make that last number factorial. And then those cancel out. And so all you have to do in your calculator is 14 times 13 times 12 times 11. Alright. And so when you do that, you should get 24,024. Now, how many different ways can a committee be appointed? 4 people. Now, with a committee, it doesn't matter who the first, second, third, and fourth committee members are. It's still the same committee. So, you know, you're on the committee, I'm on the committee, your friend's on the committee, and my friend's on the committee. That's 4 people. Well, if I took those same 4 and I was to say, okay, your friend's on the committee, my friend's on the committee, you're on the committee, and I'm on the committee. It's the same 4 people. And it's actually the same group. So that means it's going to be a combination. We're not counting those as different groups. Alright. So if this is a combination, then it's going to be 14 factorial divided by 14 minus 4 factorial times 4 factorial. We have to put that number we're selecting again here on the bottom. So it's really going to be what we just got divided by 4 factorial, because 14 factorial divided by 10 factorial we've already figured out is 24,024. So you could just say 24,024 divided by 4 factorial. But you should get 1001 when you do that. Right. What is the probability of randomly selecting the committee members and getting the 4 youngest of the qualified candidates? There's only one way you could select 4 youngest. Out of thousands and thousands, if you selected 4 youngest, there's only one way to select the 4 youngest. We don't know who the 4 youngest are. There's only one way to do that. So that's why it's a 1 out of 1,001. And the last problem. When testing for current in a cable with 10 color-coded wires, the author uses a meter to test 4 wires at a time. How many different tests are required for every possible pairing of 4 wires? So, let me show you. Let's say instead of 10 colors, I had 10 letters. So if I chose the letters A, B, C, and D, these are 4 wires. This will be the same if I chose B, C, B, A, C, and D. Or if I chose D, C, A, and B. And so on and so forth. All those are the same group of wires. So that means this is a combination. So if this is a combination, we have 10 total, and we're selecting 4. So, this is probably not 50. 10 total, and we're selecting 4. 10 minus 4 factorial, 4 factorial. Combination. Alright, so that's 10 factorial divided by 6 factorial times 4 factorial. 6 factorial times 4 factorial is not 24 factorial. So 10 factorial divided by 6 factorial divided by 4 factorial, 210. That's your answer. And that's the end of test 2.